Okay, so here's the notes for ionic bonds. So just a little review. Remember, we have our squiggly line, everything to the left of the squiggly line except for hydrogen or metals, and everything to the right are nonmetals. So an ionic compound is one metal and one nonmetal. Now if you remember valence electrons from last unit, okay, let's work off of that. Okay, so oxidation number was introduced last unit. It's basically the charge, the most likely charge that an atom will take. Remember group 1 valence electrons. Group 1 have one extra valence electron, so they want to get rid of it. If you lose a negative, you have a positive 1. Next one, group 2 has 2 valence, so they're going to get rid of those 2, resulting in a 2+ charge. Skip the transitions because they can do different things. Group 13, they can lose different numbers. Group 13 ends in S2P1. Remember, so they lose those outer 3, take on a +3 charge. And skip group 14 because they can do a little bit of both. Group 15 has 5 valence electrons, so in order to form an octet, it wants to gain 3. So 3 negative charge. Group 16 has 6 valence electrons, so it wants to gain 2, so thus resulting in a -2 charge. Group 17, -1 charge. And on your periodic table, it looks something like this. So what I would do is write these oxidation numbers down on your periodic table so that if I say, hey, what's the most likely charge of calcium? It's 2+, or the most likely charge that phosphorus takes, 3-. Here's kind of our roadmap here. Last unit we dealt with covalent compounds with the LEDs. We identified polar and nonpolar. This we're going to do ionic, binary, and polyatomic. So I'll give you the definitions of those in a little bit. Okay, so first of all, let's identify an ionic bond. It's the electrostatic attraction of a cation, which are positively charged, so remember the metals, and an anion, negatively charged. Okay, so cation, as we said, are metals. Just a few examples here. And remember, it's the left side of your periodic table, left of the squiggly line. Anions, remember they form negative charges, and you simply, again, find those by looking on your periodic table. Okay, so this next slide and this slide and then the slide after that, these are for honors chemistry. So if you're CP Chem, just skip the next, this slide and the next slide. All right, so honors chem, ionic compounds form a lattice structure. Okay, and lattice would be alternating. If you look down here in the lower right, positive, negative, so on and so forth. Okay, lattice energy is the energy released when 1 mole of ionic crystalline structure is formed from gaseous ions. So let me make a little more sense out of that. Okay, if we have solid, liquid, and gas, so the solid, liquid, and gas, gas would be the highest energy. Okay, so when a gas, in order for you to go from a gas to a liquid or a gas to a solid, energy has to be released. Okay, and so that's what they're talking about. Energy released when 1 mole is formed from gaseous ions. Okay, the more energy released, typically the stronger the bond. Okay, and as you can see here, magnesium oxide has the most lattice energy, therefore most energy released when it's formed from gaseous ions, so that would have the greatest lattice energy. The next slide, again, is for honors chem. We'll look at 2 properties. Okay, so there's basically, again, this is for honors chem. There's 2 properties that increase the lattice energy. Okay, first of all is the atomic radius. Okay, so if you have 2 atoms, well, first of all, increased lattice energy. 2 things that contribute are the smaller the radius, the greater the lattice energy. So, for example, if you have 2 atoms that are very large versus 2 atoms that are very small, the 2 small atoms are going to be closer together. Okay, so the reason it increases with a smaller radius is because simply they're closer together, forming a stronger bond. The next one is greater net charge. So the more positives an atom has, or the more negatives an atom has, it's going to bond stronger to other atoms that are of opposite charge. So it says which has the greatest lattice energy, MgO or CaO. Remember in the lower left-hand corner, those are the elements with the greatest lattice energy. With the greatest atomic radius. So whichever one's closest to the lower left is larger. So Ca is closest to the lower left, so it's larger. MgO, so here's CaO, we'll put larger. MgO is smaller. Okay, so MgO is going to have the greatest lattice energy because it's simply smaller. Next one, which has the greatest lattice energy, AlCl3 or MgCl2? Well, this one does because simply Al has a 3 plus charge, Mg has a 2 plus charge. Okay, so this is back to CP and honors. Binary ionic, bi means 2. It has it's a compound composed of 2 types of elements. So a cation and an anion. The cation is always listed first, so we have Na and Cl, 2 types. We have Mg and Cl, 2 types, K and S. Okay, so those are all binary ionic, metal, nonmetal. Formula units, this is the smallest formula for an ionic compound. Whenever we write these formulas, it's basically the formula of an ionic compound in reduced form. So if you look at all 3 of these, they're all written in lowest whole number ratios. Okay, so opposites tracked here. So let's look at Na plus and Cl negative. Okay, for every 1A, it's going to attract 1 Cl negative. Okay, and the key is they have to come together and neutralize each other. Okay, so they have to be in that ratio to where the positives equal the number of negatives. Let's look at the next example, Mg2 plus and Cl negative. Well, if we have Mg has a 2 plus charge and we have Cl1 negative, if we have one of each, the positives are not going to cancel out the negatives. So we need another Cl1 negative. Okay, and it would look something like this, 1 Mg and 2 Cls. Okay, so now what do you do with transition metals? Remember, if you look on your periodic table, there's no set pattern for transition metals. Well, what you have to do on the back of your periodic table has a list of some cations and some anions. So basically, it lists the charges of those transition metals, the ones that we don't have a set pattern for on your periodic table. So if you look on the back of your periodic table, that's where that chart is. You'll notice copper can have a +1 charge or a +2 charge. Same thing with iron. Iron can have a 2 plus or a 3 plus. Okay, so what we need to do is we need to tell which one of those we have. So for example, if copper is the copper with the +1 charge, instead of putting +1, they use a Roman numeral 1. So Roman numeral means just +1. Okay. If it's copper with a Roman numeral with a 2 plus charge, it's Roman numeral 2. Okay. Well, how do we figure out what charge it was? Well, it matters what it's bonded to. If you look at chlorine, is in group 17, it forms a 1 negative. Well, that means this copper must be a +1. Here we have 2 chlorines, so that's 2 1 negatives, and therefore this one must be the +2 charge. Okay. So here's the deal. On the back of your periodic table, whenever you have a transition metal that can have multiple charges, okay, look under the cation list, and there's a whole bunch of them. Whenever you use one of those and you write the name for it, you have to make sure you put a Roman numeral for that. And I'm not going to test you on the alternate naming system, okay, which is down here, but I just wanted to expose you to it. I don't care for that naming system because it doesn't tell you the charge, it just tells you which one's the lesser of the 2 charges. Alright, that concludes binary ionic. The next video will show you how to write formulas for these binary ionic compounds. Pretty short, it's about 4 minutes long. So, alright.